Assalamualaikum and hi everyone. Our group will be presenting about transition metal and coordination compound.
This is our group members that consists of 5 members. And these are the topics that we'll be discussing about.
The objective of this video presentation are to define what transition metals are, explain their key physical and chemical properties, describe coordination compounds and how they form, lastly discuss their application in industry and biology. Moving on to introduction to transition metal and coordination compound. Transition metal are elements found in the D block of the periodic table from group 3 to 12 that can be formed for at least one stable ion with a partial field d orbitals. Next, coordination compound, molecules or ions consisting of a central metal atom or ion bonded to surrounding molecules or ions called ligands via coordinate covalent bond. These are the example of transition metal that we can find in the periodic table. For example, iron, copper, chromium, nickel, cobalt, manganese, zinc, titanium, silver, palladium, gold, and platinum.
Variable oxidation states. Transition metals can form ions with different oxidation states because of their 3d and 4s electrons have similar energy levels, allowing them to lose different numbers of electrons. For example, iron can exist as Fe2+ and Fe3+. Manganese shows several oxidation states such as +2, +4 and +7, and copper can form Cu+ and Cu2+. Next is color compound. Many transition metal compounds are colored due to D to D electronic transitions. When the light is absorbed, electrons move between the d orbitals and producing a color. For example, the complex copper hexa aqua CuH2O 6(2+) appears as blue, while iron thiocyanate FeSCN2+ forms a blood red color. For magnetic properties, transition metals often have unpaired electrons, which make them paramagnetic. For example, Mn2+ is paramagnetic due to several unpaired electrons, while Zn2+ is diamagnetic because it has no unpaired electrons. Besides that, for catalytic abilities, transition metals are good catalysts because they can easily change oxidation states and form temporary complexes. For example, iron is used in the Haber process to produce ammonia, while nickel is used in the hydrogenation of alkenes. Therefore, these properties make transition metals very important in the industrial processes.
Now I will explain what a coordination compound is. A coordination compound is a compound that consists of a central metal ion, which is usually a transition metal, surrounded by molecules or ions called ligands. These ligands donate a lone pair of electrons to the central metal ion. Because both electrons come from the ligand, the bond formed is known as a coordinate bond, also called a dative covalent bond. So in coordination compounds, the metal ion acts as an electron pair acceptor, while the ligands act as electron pair donors. For example, in the complex ion CuNH3 4 2+, the central metal ion is Cu2+, and the ligands are 4 ammonia molecules. Each ammonia molecules donate one lone pair of electrons to the copper ion, forming 4 coordinate bonds. This results in a stable coordination compound. Next, let's talk about the central metal ion. The central metal ion is usually a transition metal ion, and it behaves as a Lewis acid, which means it accepts electron pair of ligands. The central metal ion plays an important role because it determines the oxidation state of the complex, the coordination number, and also the geometry or shape of the complex. Common examples of central metal ions include Fe2+, CO2+, and others. Now, let's move on to the ligands. Ligands are molecules or ions that surround the central metal ion in a coordination compound. They must have at least one lone pair of electrons to donate to the metal. Ligands can be classified based on the number of donor atoms they use to bond with the metal. First, monodentate ligands donate one donor atom. The example include water. Next is bidentate ligands donate two donor atoms. A common example is ethylene diamine. And lastly, polydentate ligands donate more than two donor atoms. Examples include EDTA, which can form very stable complex. Here is an example of coordination compound CONH3ClCl2. The part inside the square bracket is called the complex ion. In this complex, cobalt is the central metal ion, 5 NH3 molecules and 1 Cl- ion are the ligands. The two Cl ions outside the brackets are known as counter ions. The counter ions balance the overall charge of the compound but are not directly bonded to the metal. Next, let's discuss coordination number. The coordination number is defined as the number of ligand donor atoms directly bonded to the central metal ion. Common coordination numbers are 2, 4, and also 6. For example, here we have AgNH3 2+ has a coordination number of 2. Next is NiCO4 has a coordination number of 4, and the last one is CONH3 3+ has a coordination number of 6. Finally, let's look at the geometry shapes of coordination complex. The geometry of a complex depends mainly on its coordination number. When the coordination number is 2, the geometry is commonly linear, such as in AgNH3 2+. When the coordination number is 4, the geometry can be tetrahedral or square planar, for example, NiCO4. When the coordination number is 6, the geometry is octahedral as seen in CONH3 6-3+. In conclusion, coordination compounds consist of a central metal ion bonded to ligands through coordinate bond. Their properties, coordination number, and geometry depends on the metal, ion, and the type of ligands involved.
Hi everyone, so I'll be explaining about the crystal field theory and how it helps us understand the color and magnetic properties of transition metal complex. So, the crystal field theory explains what happens when ligands approach a transition metal ion. Lone pair of electrons from the ligand interacts with the d orbital of the metal ion. This interaction causes the d orbital to split into different energy levels instead of remaining at the same energy. In an octahedral complex, the 5d orbitals split into two groups. The first one is the lower energy orbital called T2g, which are dxy, dxz, and dyz. And the second one is the higher energy orbital called Eg, which are dx square, y square, and dz square. The energy difference between these two groups is known as crystal field splitting energy, or delta O. Do you know how we can actually see colors? So actually, when white light shines on a complex, some of this light is absorbed. An electron is promoted from the lower energy T2g orbital to the high energy Eg orbital. The remaining light that is not absorbed is what gives the complex its observed color. Okay, moving on. Different ligands cause different amount of splitting. weak field ligand, such as water, cause a small energy gap and usually produce pale colors and high spin complexes. While on the other hand, strong field ligands such as cyanide cause a large energy gap, often leading to low spin complexes and different colors. For example, the complex hexacuron 2 ion appears pale green because water is a weak field ligand, while ferrocyanide ion appears colorless or very light in color because cyanide is a strong field ligand that causes large splitting.
Hi everyone, my name is Nur Shakira Husna. So now I will be explaining about the applications of transitions metals and coordination compounds. Transitions metals and coordination compounds have many important real-world applications. In industry, iron is used as a catalyst in the Haber process to produce ammonia, which is essential for fertilizers, and platinum is used in catalytic converters in cars to reduce harmful exhaust gases. In medicine, cisplatin, a platinum coordination compound, is used to treat cancer by damaging cancer cell DNA. EDTA is used in chelation therapy to remove heavy metals from the body. In biology, hemoglobin contains iron that binds oxygen for transport in our blood, while vitamin B12 contains cobalt and is important for metabolism and nerve function. So now, moving on to the why coordination chemistry matters. Coordination chemistry is important because it explains color formation in transitions metal compounds, which happens due to electron transitions in split d orbitals. It also predicts magnetic properties by determining how many unpaired electrons are present in complex. Coordination chemistry controls reactivity and stability, allowing chemists to design effective catalysts and stable compounds. It enables biological functions such as oxygen transport in hemoglobin and enzyme activity in the body. Finally, it supports industrial process including fertilizer production, fuel refining, and pharmaceutical manufacturing. In conclusions, transitions metals are unique because they have variable oxidation states from colorful compounds and show strong catalytic properties. These special characteristics allow them to participate in many important chemical reactions. Coordination compounds helps explain the bonding, structure, and reactivity of transitions metal complexes, making it easier to predict their behavior. As a result, transitions metals play an important role in industry, medicine, and biology, including manufacturing process, medical treatments, and essential biological functions. Overall, understanding transitions metals and coordination chemistry helps us connect chemical theory with real-world applications. That's all from me. Thank you.
So here are the references that we use along the presentation. Thank you everyone.